In these slides, we want to study the origin of Kirchhoff's voltage law. So let's go back to the chapter on potential and remember that the potential difference between any 2 points in space, point 1 and point 2, to find the potential difference, you need to create a contour and integrate E dot dr along this contour. And we showed that it doesn't depend on the path that you choose, and that the potential difference V2 minus V1 is minus integration from 1 to 2 E dot dr. This is from the chapter on potential, so if you can't remember this, you should go back and remember and revise this part. What if we make the contour go around in a closed loop? So points 2 and 1 are very close to each other, almost on top of each other. And so now when you integrate from 1 to 2, you're going from here all the way around the closed loop and you go back to the same point. So the potential difference between a point and itself is 0. So that means that when you integrate over a closed loop, the circle now means a closed loop, E dot dr, you get 0. And this electric field we're talking about is the electric field due to static charges. There's another kind of electric field we'll take later on in the last chapter of the semester, which is a non-conservative electric field which doesn't behave. But for a static electric field due to static charges, which is called a conservative field, when you integrate the electric field over any closed loop, it's always equal to 0. So we're going to modify this equation. Is not always correct. It's only correct when there are no time varying fields. Later on, we're going to generalize this equation and include other kinds of electric field, another kind of electric field, non-conservative field, and we'll see what the left-hand side will change to in that case. But for now, we're talking about static charges only. We don't have any time-varying fields, and so if you integrate the electric field over any closed loop, you get 0. This is the origin of Kirchhoff's loop law. So let's give an example. Let's say you go around the loop clockwise, so that's why I put the arrow here going around clockwise. And let's say you have a circuit like this. It consists of an EMF, source of EMF, U epsilon 1, a battery, and we're going to explain what EMF is in more detail soon. But for now, let's say you have a battery that has a certain potential difference across its terminals, and you have a resistance, another battery, and so on. Any kind of elements you have in a circuit. How would you apply this rule for this circuit? You have to go around the loop in a particular direction. We chose here to go around clockwise, but you can go anti-clockwise. It doesn't make a difference. And you go around the loop and you integrate the electric field dotted into the element of length for the whole loop. So you go from A to B, and then you go from B to C, and then you go from C to D, and then you go from D to E, and then you go from E to F, and then you go from F to G, and then you go from G to H, and then you go from H back to A. So you make a complete loop. And this integration, based on this equation, it should all give you 0. But let's look more carefully at each one of these terms. What is this term? What is this term? What is each one of these terms independently? This term is just the potential at A minus the potential at B. And this term is just the potential at B minus the potential at C. And this term is just the potential difference between C and D, and so on. So these integral of E dot dr can be written as potential differences across all the elements. We can substitute then by these potential difference, and you notice that everything will cancel as you expect, and you get 0 because you have here minus VB plus VB. You have minus VC plus VC, minus VD plus VD, minus VE plus VE, minus VF plus VF, minus VG plus VG, minus VH plus VH, minus A and A. So obviously when you add all these you get 0. So this is basically Kirchhoff's voltage rule, and it comes from this fact that if you integrate the electric field due to static charges over any closed loop, you get 0. So we can rewrite Kirchhoff's voltage rule like this: the sum of all the potential differences across all the elements. I here goes from 1, the first element, to the nth element that you have in the loop. There could be any number of elements. And you have to go around the loop in a particular direction, the way we did it in the previous slide. You get VA minus VB, and then B minus C, and then C minus D, and so on. You have to go in a particular way to go around the complete loop. When you add all those potential drops, you should get 0. So the next step that we want to follow is to learn how to get the potential drops across different elements in a circuit. A battery, if you have a battery with a certain EMF, and we'll discuss EMF then in detail and explain what it means. How would you get the potential difference across a battery, an ideal battery? How would you get the potential difference across a resistor, depending on the direction of the current? So this is the next thing we're going to tackle right now.